Hi, folks. In section 10.2, we're going to learn about box and whisker plots. And box and whisker plots are one way to represent the variation among a particular population. For instance, the heights of various females in high school, or the shoe sizes of various men on a basketball team, or speeds of different cars on a highway, where you have multiple measurements, um, and you want to kind of compare the variation among that data set. And so the box and whisker plot is called a box and whisker plot because you can see that there's a box. There's a whisker on the left side, there's a whisker on the right side, um, and we're going to learn how to draw these today. So the box and whisker plot depends on a few important values. It depends on the least value is going to get graphed, and the greatest value in the data set is going to get graphed. The median will be graphed. And the median is just that center value. We learned about it in 10.1, where you list all of the values in order, and it's that center number if it's an odd number of values in the data set, or it's the average of the two center numbers if there's an even number of values in the data set. We're also going to think about the first quartile and the third quartile. So the median is also called the second quartile. Quartile just means you've divided the data into 4 sections. And so that second quartile is just called the median. It divides the data into two halves. And the first quartile is going to be kind of like the median again, but just for the first half of the data set, the lowest half of the values of data. And then the third quartile is going to be the median for the upper half of data. So we're going to divide our data into 4 equal sections, and we're going to have a representative value between the first and second set, that's the first quartile, between the second and third set, that's the second quartile, and between the third and fourth set, that's the third quartile. These 5 values that I've got circled in blue here, our textbook calls the 5-number summary. The least value, quartile 1, quartile 2, quartile 3, and the greatest value. Just so that they don't have to name all 5 of those. They call it the 5-number summary. And then later on in this chapter, we will talk about the interquartile range. Last section, we learned about how the range was just the largest value minus the smallest value. But we'll see today that sometimes those largest and smallest values are very extreme. And another way to kind of measure the range of data is to look at the interquartile range. Look at just the difference between the Q3 value and the Q1 value. And that kind of then ignores any extreme values you have at the end. You're looking at just the variation in the middle half of the data set, because 50% of your data exist between, inside the box. 50% of the data points are represented by the box here in a box and whisker plot. So let's look at how to draw one of these and how to go about finding these different quartiles. So we're supposed to make a box and whisker plot representing the ages of members of this backpacking expedition. So in order to make a box and whisker plot, we need to have the values listed in numeric order. That's the only way we can find the median. And then also to find quartile 1 and quartile 3, we also need all the values written in order. And this is often the longest part of the process, especially with bigger data sets. If you have a really big data set, it's best to do put it on Excel or some other spreadsheet program like that, where you can sort the data. The computer will sort it for you in numeric order. Looking on here, 18 seems to be my smallest value. And then I see 22 and 22 twice. Then I've got 24 and 25 3 times. So there's my 24, 25, 25, 25. Then I have 27, 28, and I have 33 times. So I have all the numbers accounted for, and I've listed them in order. And now I can think about my 5-number summary, because these are the 5 numbers I'm going to need to put in my box and whisker plot. So first of all, I want to think about my lowest number and my highest number. And I want to make sure these are all encompassed on my number line here. So I'm going to go 17, 18, 19, 20. You can actually just start with 18. You can start with the lowest number. I just happen to know that this data line is longer than what I need it to be. 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I've already gone plenty high because my highest value is 30. I'm going to go ahead and plot the 18, and I'm going to plot the 30. So I've plotted my extreme values. Next, I'm going to think about my median. My median is my middle value, and this data set has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 values. It's an even number of values. So my middle value is going to be kind of between values 6 and 7 here. And the average of 25 and 25 is just 25. So that's going to be my middle value. And I'll draw that as a vertical line. And now that's my median. I need to think about my quartile 1 value and quartile 3 value. So what I want to do is that median kind of cut my data set in half. And I want to find the center value of the lower half and find the center value of the upper half. So I want to find my middle number here. Well, my middle number is, because I have 6 data points here, the middle value, I've got an even number. So positions 3 and 4 are my 2 middle values. So I'm going to need to average those. That average number is going to be 23. And then my average value up here is going to be, my Q3 value is going to be my middle point up here, which is halfway between 28 and 30, which is going to be 29. So I'm going to have a box that goes from 23 up to 29, like that. So notice I graphed my 23 value, my 29 value, and to use that Q1 and Q3 to draw my box. And then my Q2 value, or my median, is the line in the middle of the box. I have a box now, but it's not a box and whisker plot until I attach the whiskers on to either side. And this now is the box and whisker plot that represent this set of data. So again, the first step is ordering the data, finding the median, finding the quartiles, drawing a number line that includes the least and greatest values. And above the number line, I plotted the least value, the first quartile value, the second quartile value, the third quartile value, and the greatest value. I use the first quartile and the third quartile to draw the box. I have a vertical line representing my median, and I drew whiskers out to each extreme. What if you're given a box and whisker plot? How do you interpret information represented to you in that box and whisker plot? So here I've got a plot representing the lengths in seconds of songs played at a rock concert. So it says find and interpret the range of the data. Well, from a box and whisker plot, I can see what my greatest value is, and I can see what my least value is. So I can calculate the range. The range is the greatest value minus the least. Greatest minus least, which is going to be the 300 value minus 160, and that's going to be a 140-second variation in song length at the concert. Okay, So we found the range, and we also interpreted what that range means in the context of this problem. It says describe the distribution of the data. So here we remember 50% of the data are encompassed in the box portion of the box and whisker plot. And then 25% are on each whisker. So I've got 25% of the songs are here, 25% of the songs are here, and then 50% of the songs are in the box. So I know that 25% of the songs were between 160 to 220 seconds. And then I know 50% of the songs were between 220 seconds and 280 seconds. And then I know that 25% of the songs are between the 280 seconds and the 300 seconds. So we kind of have a sense of where most of the songs fell in terms of their song length. The next question is asking us to find and interpret the interquartile range of the data. Remember, the range is when you subtract the extreme values, the very biggest minus the very smallest. The interquartile range is when you just do Q3 minus Q1. So this value here minus this value here, the edges of the box. So I'm going to do 280 minus 220, and that's a 60-second kind of range in song length. So the middle 50% of the songs varied by no more than 60 seconds. Okay. So the vast majority of songs were all pretty close to, I mean, this is centering around, that's a little less than 4 minutes. That's a little more than 4 minutes. So kind of really centered around that length. The middle 50% of songs varied by no more than 60 seconds in that kind of 4-minute-ish range. The last question asks, are the data more spread out below Q1, below the first quartile, or above Q3? Basically, what we're looking at here is the length of the whiskers. So below Q1, look at how long that whisker is compared to above Q3. Look at how short that whisker is. So this is kind of telling us the longest songs, the longest 25% of songs didn't actually vary that much in length. We didn't have any kind of like 10-minute songs or anything like that. But the shortest 25% of songs, there was a bit of variation. The shortest one was about 2.5 minutes long, a little bit more. And so the data, because the left whisker is longer than the right whisker, which means data below the Q1 are more spread out. More spread out than the data above Q3. So the length of the whisker kind of represents how spread out or not the data are. So before we move on to the next question is going to ask us to kind of compare shapes. So let's look at this key idea here first. You can have symmetric box and whisker plots, which are, approximately balanced on each side, where the whiskers are about the same length and the median is kind of in the middle of the box. Then you can have skewed left data. Skewed left means that your left whisker is longer than the right whisker. Skewed left means most of the data are actually piled up on the right side of the plot. But I like to focus on that left whisker because left whisker, skewed left, the terms kind of go together. And of course, the opposite of that is being skewed right is when your right whisker is really long. And so most of the data are kind of piled up on the left side of the plot. So let's look at a couple of pre-made whisker plots and look at how to interpret the data. So here we're looking at test scores in my class versus my friend's class. So I've got two box and whisker plots representing what's happening here. And it wants me to identify the shape of each distribution. So I'm going to have my class, and then I'm going to have my friend's class. So for my class, the shape. If I look at my class seems to have a long left whisker and a short right whisker. But because my left whisker is long, I've got a long left whisker. This means my class's data is skewed left. Most of the class data in my class is on kind of more the right side of the graph. Um, if I look at my friend's class's data, friend's class, I can see that they've got kind of equal length whiskers on both sides of the box, and their median seems to be in the middle of their box. So they have a symmetric, the whiskers are equal length. Whiskers are equal, and this is a symmetric distribution. Okay. So that's how I would kind of describe the shapes of each distribution. The next question is asking me which set of scores is more spread out. So this is my class again is written in blue. If you look at the kind of range of data, uh, my range of data just goes from 70 to 100. So my range is from 70 to 100. So 100 minus 70 is 30. You can also look at the interquartile range, which is sometimes more appropriate for skewed data, is looking at the interquartile range, is 95 minus 85. And that is a difference of 10. On the other hand, if I look at my friend's class, their range goes from 100 all the way down to 60. So 100 minus 60 is 40. And their interquartile range is between 90 and 70. Remember, we're looking at the edges of the box there. So 90 minus 70 is 20. And so whether I use the range or the interquartile range, I do see the same results. I see that my class has uh, less spread out data. And I see that my friend's class has more variation. Their data are more spread out. Okay. All right. The manager lists batting averages for players on a baseball team. Make a box and whisker plot that represents the data, describe the shape of the distribution, and then we're going to look to see if the data set contains any outliers. So we'll practice one more time doing a data set. And once again, the most time-consuming portion of this is often just kind of listing the batting averages in order. So 0.174 is the lowest, 0.210, 260, 0.264, 0.276, 0.280, 0.290, 0.295, 0.311, 0.325, 0.380, and 0.406. In this example, 9, 10, 11, 12. Yeah, we've got 12 values. So I've got my least value, my greatest value are easy to spot. My median, my middle number, or my Q2 value, is going to be halfway at the average between 0.280 and 0.290. So that's going to be 0.285. And then I need to find quartile 1, which is going to be the average of these values. Quartile 1 is going to be 0.262. And then my average between these values, 0.311 and 0.325, is going to be 0.318. My quartile 3 is going to be 0.318. So if I plot these data above my number line here, my extreme values are 0.174, which is almost kind of halfway between here and here, between 0.150 and 0.2. 0.406 is just over the 0.4 value, so I'll put a dot there. And now I can focus on graphing the first quartile is 0.262, so maybe around here. And my quartile 3 value is 0.318, so that's going to be around just less than 0.32. Okay, so I'll make a box with those two numbers, and I need to plot my median, 0.285, so that's around here. And then connect my whiskers. And there is a box and whisker plot. We've drawn the box and whisker plot that was requested, and we're asked to describe the shape of this distribution. Well, my two whiskers seem to be about the same size, and my median seems to be kind of in the middle of my box, and so this does appear to be a symmetric distribution because of those whiskers are equal length. Okay. And also because my median is in the middle. The question is, does the data contain any outliers? Now, in section 10.1, we just kind of eyeballed it. We said, ooh, that one price, like wage per hour, seems a little high compared to everyone else's. That must be an outlier. Using your own subjective judgment for judging outliers isn't very scientific. It isn't reliable. People can just kind of decide, I'm going to throw out that number just because I feel like it. So it'd be nice to have a better hard and fast rule to follow to identify outliers. And the textbook suggests that using the interquartile range to kind of calculate an acceptable value past which we consider something to be an outlier. So what we're going to do is we're going to find the interquartile range and we're going to multiply it by 1.5. So let's do that first. We're going to find interquartile range and multiply by 1.5. So what is my interquartile range? My interquartile range is the difference between Q1 and Q3. So that's 0.318 minus 0.262. And when you do that subtraction, you get 0.055. And we're going to take that value and we're going to multiply times 1.5, and that's going to give us an answer of 0.0825. We're going to take this value and we're going to subtract it from Q1. And then any values that extend further to the left than that cutoff value, we're going to call an outlier. So we're going to do Q1 minus this 1.5 times the interquartile range that we just figured out. So we're going to do 0.262 minus this number that we just calculated, the 1.5 times the interquartile range. So that's 0.0825. That's going to give us a lower end value. And that answer is 0.1795. So any values that are lower than 0.1795 are considered to be outliers. So if we look at this data set, are there any values that are less than 0.1795? Yes, there are. We're going to consider that 0.174 value is an outlier. Okay. We're going to do the same thing on the upper edge of the data. We're going to take that 0.0825 value that we calculated, and we're going to add it onto our Q3 number. And any value that's so extreme, it's even higher than that cutoff value, we're going to call an extreme value, an outlier, and we're going to remove it from the data set. So we're going to take our Q3 value and we're going to add that 1.5 times the interquartile range that we calculated. So our Q3 value is 0.318, and our 1.5 times the interquartile range was this 0.0825. And when we add that together, we get 0.3995. So that's our kind of cutoff value. If we look on this list and we see any values that are more extreme than 0.3995, then we exclude them from the data set. And in this example, we find that 0.406 is an outlier. So rather than just making kind of a subjective judgment call on this, we're using a fixed rule to decide what data in the data set are outliers, and then we can exclude them from further analysis if we're trying to find, mean or median or mode or something like that. So 0.174 is an outlier, and 0.406 is an outlier according to this rule. I hope this helped.